All right, welcome back, B's and G's, to a long, no-D version of Drive-Thru Confessionals. Hungry? Stop at the deli. Make yourself a sandwich. Okay, today we're going over the 5-2 homework from last night, and we will be introducing 5-3, which is virtually the converse of everything you learned how to do yesterday. Here comes my boss. Morning, Doc. Yeah, I'm recording this so I can just play it for my fifth bell class because I won't be here today. We'll see how it works. I will. Thank you. Good luck. Thanks. All right. There are no interruptions to the drive-thru. We just forge forward and take orders. So we're going to go over the warm-up. In order for these two lines to be parallel, these are alternate what? Interior angles. And how must they be related if the lines are parallel? Lukey? They would be congruent. So we're going to say x squared plus 4x is equal to 20x plus 36. The geometry of the problem's over. Now it becomes an algebra problem. I noticed a lot of you used quadratic formula to get it, which is fine, but it took you too much time. Always try to factor first. So I got to set everything equal to 0. So that's going to give me x squared, 4x minus 20x is a negative 16x. And minus 36 equals 0. So before you go right to the quadratic formula, you should ask yourself a little riddle. You're looking for two numbers that multiply to give you negative 36, and that add to give you negative 16. So if numbers multiply to be negative, one of them has to be negative, and the other has to be positive. And it's not the easiest factoring that there is, but do you remember that 18 times 2 is 36? We want it to add to be negative, so it's going to be a negative 18 and a positive 2. Therefore, x is equal to, class, positive 18 or negative 2. Well, now we got to pop them in and see if they are both possible solutions for this geometry problem. So you can put them in on either side. The results are equal, so it doesn't matter which side you put it in. I'll put it in on the 20x side, so 20 times 18 plus 36. Oh dear. That's going to be really big. What'd you say, Quinn? Okay, so that's 396. All right, and now let's try to put in the negative 2. So it gives you negative 40 plus 36, which is negative 4. Interesting. So neither of those can be angles, but in order for this to be true, that would be our values for x. So I guess in this particular problem, the maker of the problem, which is your book, this was the suggested warm-up problem for the day, didn't really take into context that these angles would not be realistic, because you can't have a 396-degree angle. So not a totally good warm-up problem, yet a good chance to practice some algebra. Any questions on that one? Okay. How many of you use quadratic formula? Okay. Okay. You actually did complete the square? E? Okay. All right, now homework questions. Quinn. All right, 17. Write a valid inequality and find the restrictions on x. So Jody, this kind of satisfies one of the questions you wanted me to cover. We've got an angle inside 30 degrees, and we've got an angle outside that is 3x minus 18. And based on what we learned yesterday in that first strange theorem, the exterior angle must be greater than either of the remote interior angles. So either of those two. So our inequality is that 3x minus 18 must be bigger than 30 degrees. Okay? That's the inequality. And then the restrictions on x, all we have to do is solve that equation for x. Solve that inequality for x. So add 18. You get 3x is greater than 48. Divide each side by 3. You get x is greater than 16. Does that make sense? Jazz? Yes, I'm sorry. You would have to do, actually, you have to do 3x could it be, yeah, that would be the other side. Sorry, so 3x minus 18 is less than 180. Add 18. Divide each side by 3. And you get x is less than, is that 66? Okay, so we would write that as x is greater than 16 and less than 66. Thank you. Thank you. All right, what else? Luke, 21. Okay, yeah, this is a good way to test your knowledge, because this is a really quick proof. If you do it one way, Luke, it takes a little bit longer to do it the other way. There's two different ways we can prove these lines parallel. So we've got MOPR, and then given to us, well, here, let's just start. I'll just write it right inside of our proof. Angle MOP is a right angle. Okay? And we're also given that RP is perpendicular to OP. And we're being asked to prove that MO is parallel to RP. We know that MOP is a right angle. At this point, I just want to think about the verbiage, the wording on our last theorem from yesterday. So it was a theorem to use to prove two lines parallel, and it said if two lines are what? Perpendicular to the same line. So what I want to do is get two lines perpendicular. Well, I already got one pair of lines perpendicular, so I've shown that RP is perpendicular to OP. So now I'm going to say that MO is perpendicular to OP. Do you remember what my reason would be for that? We haven't done this in a long time. Definition of perpendicular. What's up, Jason? You can come on by. It's just a drive-through, buddy. All right. Who dat, baby? Okay, so that's the definition of perpendicular. If you remember, if two lines intersect to form a right angle, then those two lines are perpendicular. Okay? So look, now we've got RP is perpendicular to OP, MO is perpendicular to OP. They're in the same plane because we have a picture. That is our plane. So now we can go right to the end and say that MO is parallel to RP. And that's when we're going to use the if two lines are perpendicular to the same line, then they are parallel to each other. Does that help, Luke? Okay. Jody? 22. Find the restrictions on X. And then it says, I'll go into that a little bit more here. So we've got, hey Jace, are you going to watch the Bengals game today? All right, buddy. It's going to be on pretty late, though. All right, virtual knucks from here, and then we'll all give you a peace out. Boom. I can't make it that far. I'm wired in today. See ya. What do you guys say to Jason? Peace out, Jace. Thanks, buddy. See ya. All right. And then we got, yeah, Quinn? Exactly. But to get to say that they were congruent, you would have had to say that was a right angle, and then you'd have to say these two angles are congruent by right angle congruence. So yeah, that's the other way to do it. And same side interior. Did that take you 4 steps or 5? Okay. Everybody catch that? That was kind of quick. No? Did you catch it? Okay. We're getting to the point where these proofs can be proven so many different ways. Somebody proved the last question on the test in 19 steps. It was totally correct. Okay? But it just becomes difficult to grade. That's why you don't have your test back yet. So I have to grade each one individually. Okay, back to the homework. We've got an 81 here. We have an X degrees here. And a 37 over here. Okay? And it says, Jody, that point, let's see, L, K, P, M. It says that point P can be anywhere, which basically means don't assume that X is obtuse or acute. It can be anything. Okay? So, we know that X is definitely bigger than 81. That's from our exterior angle theorem that we learned first. That said, let me get some highlighters here. Ignore segment LM for now. Okay? Says the measure of an exterior angle is larger than either of the two remote interior angles. Uh-oh. Okay? That's what that means. That's where I got X is bigger than 81 from. Now we got to figure out what X is less than. Well, we know that this is 37. Okay? This cannot be 0, but it can be close to 0. It could be 0.00001. We just know it has to be bigger than 0. So we know that X has to be less than, well, what I would do to find out the sum of these two angles, this one and this one, is do 180, because the sum of a triangle, minus 37, and you get 143 degrees. So this angle here could not be 143 degrees, because that would make this angle 0. But it could be 142.9 degrees. That would make this angle 0.1. So what that means is X has to be less than 143, and then we would rewrite it like this. X is bigger than 81 and less than 143. And that's a question without a lot of work that is not easy at all. Correct. Correct. Okay? Yee. 0. So you had a 0 here. Is that what you're telling me, Yee? So let's see if you might be right. If it could be 0, then it could be, you're saying it could be 1 degree. The problem with that is, if you're saying that this was 1, you've now broken the triangle exterior angle theorem that we learned yesterday, that said that the measure of an exterior angle is greater than either of the remote interior angles. So that's why that 0 wasn't right. Does that help? Okay? Ashlyn, is that the one you're going to ask about? Any other questions on the homework? Steph, 24. Okay, this is great. It does make a mention to you in this one, Stephanie, that you might want to look at example 2 to figure out how to say that something's a parallelogram. So they didn't expect that you would know the definition of a parallelogram. We're going to teach that to you in chapter 7. But it gave you a hint to kind of look back and get some help. So what we're given here is something that appears to be a parallelogram. We're going to try to prove that it's a parallelogram. It's boring. A, B, C, D. This is 1, 2, and 3. And here we go. So we are given that 1 is sup to 2. And that 2 is sup to 3. And I was helping a kid after school yesterday, and she was like, oh, that means that 1 is congruent to 3. And I'm like, oh, awesome. I didn't even think of that. But unfortunately, now we have to kind of train ourselves to think a little bit differently. We're not going to use the congruent supplements on this. Since 1 is supplementary to 2, that means these pink lines must be what? They must be parallel. BC is parallel to AD. And that's the if SSI, same side interior, congruent, then lines parallel. Okay? Sorry, it is. You're right. That's terrible. Thank you, Quinn. Sup, then parallel. Thank you. Okay? That's the same mistake that I would probably make when I was taking a test. Now, since angle 2 is supplementary to angle 3, that's right, AB is parallel to CD for the same reason. Okay? And now my final step is that ABCD is a p-gram. And my reason is if a quad has 2 pairs of parallel sides, then it's a p-gram. Okay, that actually would be right. But there's going to end up being 7 different ways to prove something's a parallelogram. That's the only one that's a definition. But you're not there yet, so that's fine. Okay? All right, we good on that? All right, here's our first postulate, okay? This one. Starting to writing, because we have 8 theorems. That's right, 1 more than yesterday. Okay? Yeah, it's just a postulate. It cannot be proven. It might be used down the road. That's what postulates are for. Bless you. So if we're given the red line and the blue point, there exists only one line that is parallel to the red line that travels through the blue point. Okay? Alright, so now we're going to try to knock out a bunch of today's theorems, and we're only going to write them in shortcut form. I think you guys are going to be fine with that because that's what you prefer anyway. So yesterday, what did we learn how to do? Prove lines parallel. Today, we just flip all those theorems. And so we say if the lines are parallel, then, so we'll just get started. So if lines are parallel, then alternate interior angles are congruent. Okay, there's one. Let's see if we can just list them without looking at the book. What'd you say, Lauren? That's all right. You want to give me one? Good. If lines are parallel, then alternate exterior angles are congruent. Andrew, you got another one? Excellent. I'm going to list that as number 4, but that's a great one, okay? If lines are parallel, then, did you say same side interior, Andrew? Same side interior. We'll call those SSIs. Angles are sup. Don't make the same mistake that I made earlier and call those congruent. Now, are you asking a question, or is someone going to fill in what number 3 is? Stephanie? Okay, thank you. Perfect. So, Andrew, I just created that space because I'm keeping all the congruent ones in a section and all the sup ones in a section. So there's one more. Jode? Again, make sure you say supplementary and not congruent. That's the mistake I would make to lose a half a point. Okay, these are like the 5 major ones, just because they're so obviously related to what we did yesterday. Once I see your eyes, I'll know you've got them copied down. Then we're going to do these next 2 separately. And then I feel like I'm missing one in my head. I might have to look. Okay, ready? So the next one, again, this is very similar to one that you learned yesterday. It says, so we'll call this number 6 for today. If a line is perpendicular to one line that is parallel to another, then it is perpendicular to both. We're going to draw a picture of this one because that's confusing. Okay? So you're given 2 pieces of information in the if here. First piece of information is that you got some lines that are parallel. This is the symbol for parallel on a diagram. Okay? You'll also see, sometimes you'll see it like this. They both work just fine. Okay? And then what you've got here is a line that's perpendicular. Well, the only thing that you're given is that it's perpendicular to this one. So let's call this, nothing fun, M, A, D. So if M is perpendicular to A, and A is what? Luke? Parallel to B, then, D, then what can we deduce from this theorem? Grant? Perfect. All right, so that's kind of weird. I don't feel like we use it a lot, but they wouldn't put it out there if they weren't going to at least put it on the homework, possibly on a quiz and test. So that's number 6, and we have one more. This is kind of a transitive parallel law. So I'm just going to say the words. I won't make you write all the words as long as you understand them, and I'll just write down the shortcut. If two lines are parallel to the same line, or to a third line, then they are parallel to each other. Okay? So we write that like this. If two lines are parallel to the same line, then they are parallel to each other. I would also take transitive for that. Transitive property of parallel lines, whichever one. Remember, transitive doesn't always work. If two lines are perpendicular to the same line, then they are what? Then they're parallel to each other. So that's an example where transitive does not work. I believe that is all of your notes. Okay? Start the homework and maybe we'll do another question together.